So the first session we have now, and I'm really, really excited for this one because I don't know how many of you have worked in places where you had like the router guys and the WDM guys, and it was two different worlds and we didn't know what each other said and talked about. And hopefully to bridge that gap, we have Kent here today to talk to us about VDM for router jockeys. Give him a round of applause.
Thank you very much for the introduction. Can you guys hear me properly? Good, good. So yeah, welcome back after lunch, and it's a pleasure to be here. So I will try to give you a quick tutorial on wavelength divisioning multiplexing with focus on kind of from a routing point of view and perspective. So for all the transmission experts in here, you will find this quite basic. But I will try to do this from starting from the optics, going into wavelength multiplexing, and then finally I will go through some of the more advanced networking technologies to understand why this is now becoming a more and more important topic also for the router people. So I will conclude a little bit on that later on. But if I start by looking at from an historical point of view on the optics, I hope. Okay, that. That was green at least, but should I point it in?
Sorry.
It wasn't me at least.
No. Dennis, will you set it tilbage? Sorry. New battery though.
Oh, multiple things at one time there. Now it's working, yes. Okay, so back to my beautiful pictures here. So what this is intending to represent is how bits are traveling in a fiber. And if we go back in time, this is now representing a gigabit Ethernet signal. That you have a number of passengers in the car that travel with a certain speed, and that's how much data you can get out of that transceiver in the fiber. In order to increase the amount of data you can get out, you can of course just increase the speed. In this case now we have a 10 gig SFP Plus running 10 times as much data in the same amount of time. And then you can continue to do this up to a certain level. So basically in this case now the speed of the car represents the bit rates in the fiber. You can continue to do this at a fairly high level. However, today there are physical limitations on how fast you can run those, or basically switch the lasers on and off to represent ones and zeros. If you look at the typical client optics, you are today up to about 100 gig at the best rate for 100 gig over one fiber. Then you can use different technologies to get more out of it, but I will come back to that. If you do long distance transmission, you are typically actually only using 25 gig per carrier or per lane in order to get a decent transmission performance. So how can we then get more than those 100 gigs or 25 gigs that I'm talking about? Well, we can use different type of modulation formats. In this case now, I just increase the height of the car. So with that, I get twice as many passengers passing in that car. And in this case now, if we look at the modulation format, NRZ modulation, that is a modulation where you have 1 bit representation per clock cycle. Normally people talking about turning off and on the laser. That's not really how you do it. You have different light intensity level that represent 1 and 0. So the 2 bits that you can have is 1 or 0. So it's 1 bit representation that you can have on 1 clock cycle. If you use a PAM4 modulated signals, then you have 4 different light levels. So the lowest level is representing 0, 0. The second lowest is 0, 1. 1, 0, and 1, 1. So that means in every clock cycle you get up to then 2-bit representation, so twice as much data per clock cycle. So if we look at some of the standard client optics today on the market, the typical 100 gig LR4, for example, uses the first modulation type. So you have 25 gig direct modulated signal with NRZ, and you use 4 of those wavelengths combined it into a 1x 100 gig signal. In an LR1, you use the second technology. You use 50 gigabit per second transmission, but you have a modulation format of PAM4, so then you get 100 gig based on that. If you want to go long distance, then you actually need to use other type of technologies, the coherent technology. In this case, I show a constellation diagram of a 100 gig QPSK modulated signal. I'm not going to go through all the different technologies or details around that. I will try to make a simple version of representing what that could look like in relationship to a car. So if you are now a doctor in physics, don't come and tell me that I've represented this in a wrong way. This is trying to explain basically what it looks like. So what I do, I just make the car twice as wide. So with that, I can get more people into the car, and with that, I can get more bits per second going over it. I can continue to do this with different type of modulation format, so you can achieve different type of performance and use different amount of bandwidth. So in this case now I'm showing 2 versions of 200 gig signals and 2 versions of 400 gig signal, where I either use a QPSK modulated signal or a 16QAM modulated signal. The 16QAM modulated signal is kind of the highest that we go in pluggable optics for modulation. For high performance transponders, there are other technologies that you can use and more granularity, but typically this is what you do with the pluggable optics. So if we take the rightmost version there, 400 gig signal with, or I actually take the second one with 400 gig 16QAM, that's the standard 400 gig ZR or ZR plus optics. With that, you get the certain transmission capability, and it will use a certain amount of bandwidth, about 63 gigahertz of bandwidth. So then it will fit into a standard 100 gigahertz based DWDM solution. But if you want to run that 400 gig much longer distance, you need to get better performance out of it. Then you can change the modulation format in certain type of optics and run it in different modulation formats. You will use more bandwidth, but you can also get a significantly increased performance out of it. So that's what I try to represent with this. So by using the modulations in smart ways, you can then play around with capacity, with performance in different shapes and forms. So this will open up a completely new world in possibilities going forward also for 800 gig, because they make the standard much more flexible with a different new type of also modulation formats. So it will create better granularity for what kind of bit rates and performance that you can achieve with the optics. So it's just around the corner, I would say, the pluggable 800 gig for general availability. We expect to see them here coming out sometimes, kind of Q1, Q2 this year, so just around the corner. So that's basically how we do it with modulation format to squeeze in more data. So what do you as a router guy need to do to select the right transceiver? First part is, I promise not to walk around too much, sorry, with the cameras. So the form factor piece there, that's, I would say, a quite simple selection. If you have a router with QCP28 ports, you are limited to the QCP28 form factor. But if we look back in history, there has been a number of form factors, SFPs, FPP pluses, QCP, QCP28, QCP-DD, etc., OSFP, CP, CP2, and a number of other modulation formats. But that's kind of heavily affected by the router port that you have, what kind of form factor you can use. Then you have different technologies. I mean, you typically have, we normally refer to it as gray optics, but you can, short reach optics that you have within the data center. That is one type of optics. And then you also have the, type of optics that you use for connecting between data centers, some kind of higher performance optics normal wavelength divisioning capabilities or multiplexing capabilities. So I will come back to that selection a little bit later. And then last but not least, you also have the performance aspect to look into to make sure that you select the right transceiver. And I will come back also to why this is becoming more and more important for a router person to know and understand this. It didn't really used to be that way a number of years ago, but it's getting to that point now. So that's the transceiver piece. So that means we can now go up to, I mean, easily 800 gig today with general available technologies over a fiber by just selecting the right type of optics, an 800 gig optics. If you want to go beyond that, how do you do that? Is it possible? Yes, it is. You can do it, of course, two ways. If we look at the left picture, you just add more lanes on your road and build out more. And with that, you can get cars going in parallel. That's a great way of doing it if you have a lot of fiber. This is typically how you do it inside a data center. So if you want to connect between a router and a server, you just add another fiber. If you want to connect between two data centers, to dig down a new fiber and get all the rights away and all the construction work will be terribly expensive. So you need to use the fiber in a more efficient way. And that's where the wavelength multiplexing divisioning systems comes in place. In this case now, I show a passive DWDM multiplexer. They can come in different shapes and forms, but typically, I mean, you have a number of different channels. It can be a 4-channel max, 8-channel, and a 40-channel, for example. For passive networking, you are typically calculating it up to 40 channels. You normally don't go beyond that because the different filters will also have an inherited or built-in loss in them. The more channels, the more loss in, I mean, as a general term. This is a completely passive component. So you can use this in an environment without even power feed to get wavelength multiplexing done. However, if you want to add more technology to it to go further, then you need to start to add other components. There will be a limitation on how far data can travel. If we take the reference there with a car, if you go with a car and want to go from, I don't know, Copenhagen down to Madrid, you will have to stop and fill up with gas a number of times on the way. It's the same thing with light in fiber. The intensity of the light will decrease in the fiber when it travels. You normally talk about it in how many dB per kilometer. So a good fiber is 0.2 dB per kilometer in loss. And with that, you can then start to do the calculation on how far you can travel with the optics you've selected. What you can do is that you can add amplifiers to increase that distance. So when the light level goes down, you put an optical amplifier, increase the light level, and then you can continue to travel. Theoretically, you could do this forever. However, when you do that and add a standard amplifier, you will introduce noise to the signal. So there are a number of considerations that you need to look into when if you design a network with amplification. So the factors that are typically affecting the performance of the network are related to the power budget. That is very, very, say, highly dominant if you do a passive design. So, for example, if you want to go 40 kilometer, you have 0.25 dB loss per kilometer. You will have a total loss of 10 dB of that link. If you put a 40 channel max, it will be another 10 dB in loss. So then you will have a total loss between your router ports of 20 dB that you need to be able to deal with. So that means you need to select an optics that can handle that power budget, that has, for example, a TX power of 0 dBm and a receiver sensitivity on minus 21 dBm or something like that. So that's how you design your network when it comes to the passive networking. The dispersion part there, that's something that was very relevant in the 10 gig networks. And I mean, when the coherent technology came in, that became less and less relevant. We see that nowadays coming back a little bit in different type of access technologies with 25 gig, etc. That is very dispersion sensitive. So it's something that you need to take into consideration when you design your networks. So that's another parameter. And last but not least, we have the optical noise that is introduced with the amplifiers. So the optical noise will be, if I call it a static value, that will be dependent on how you design your network from day one. It will not be improved over time. So you already from day one need to take a decision on what do I want to use my network for long term? What kind of capabilities do I want to be able to support in the future? And then you design your network based on that. If you want to design an optimized or performance optimized network, you can use different type of amplifier technologies using Raman amplifiers rather than the EDFA amplifiers, etc., to get less noise introduced to the network and hence get the possibility to run a certain modulation format or wavelengths longer in the network. So all of those are parameters that you really need to take into consideration if you design the network from day one. So why am I talking about this with focus on router guys? Well, to explain that, I kind of have to point in that direction and talk about the traditional way of, at least how I see that this used to be done. I mean, the router guy asked the transmission team, I want a connection 100 gig from here to there. And then the transmission team took over and made sure that they realized that. The router guy normally handed over his 100 gig on a standardized interface, let's say an LR4. What the transmission team was that they did put that into some kind of transponder or muxponder. The difference between a transponder, on the bottom part there, that's trying to illustrate a transponder. You have a guy running on a bicycle, so a fairly bad performance, whatever you call it, technology. He comes to a certain point and then he jumps into a car to get better performance. So it's a demarcation point where you go from a gray optics or from an, say, short reach optics into a high performance optics. So you typically add a value, but it's a 1-to-1 ratio between the client service and the line. On the top part there, it's a muxponder. So you have a number of cars coming into that parking lot and they all jump into a bus. The cars are having some kind of limitation in this case, and then you have the bus where you can put more people inside. So a typical example of this would be having 4 times 100 gig circuit that you multiplex into a 400 gig service. So you run 400 gig wavelengths to have the most efficient transmission on the line side to utilize your fiber as well as possible. So this is the traditional way. Basically, there was a clear demarcation between the router and the transmission, and typically organizationally, it was 2 different parts of the organization. This is now changing, and it's changing due to technology evolution, where the introduction of the 400 gig ZR optics made a huge difference, because now you can get the full capability of a transponder or a muxponder built in one of those small little QCP DD plugs. So with that, you don't have any really boundary anymore between the router person and the transmission team. You put the high capacity optics directly into the router port and run that over some time of transmission gear. So that new part makes it more important for a router guy to understand the limitation and the capabilities of the transmission networks. So that's kind of why this is becoming more and more relevant for the router guys. So this is now we are at the point where we have gone through how to achieve, say, high performance point-to-point network. If you have a different topology, if you want to run a network, I mean, across Denmark, want to have flexibility to run wavelengths different ways, you build your network slightly differently. And the way you build it, so if you want to take that blue car and go out, it comes in on one fiber, the blue wavelengths will go in one direction, the yellow in a different direction, and the red in the third direction. This is now trying to represent what the ROADM does. It does optical switching, if we are now a router guy. So basically, you have 3 different VLANs coming in, and one you switch in one direction, the other one in the third direction, and the third VLAN is continuing pass through. So this is basically what the router does. The benefit, a router also, but also a ROADM in this case when it's optical. So the ROADM will make it more easy to design and run your network. So now you can take a wavelength from any of your site and go to any other site, all optical, without having anyone going out there, because you can sit remotely and configure those ROADMs so they can add and drop wavelengths or route wavelengths the way you want it to be done. They also allow you to balance the spectrum. So basically you can optimize the performance by always making sure that you have an optimized spectrum. And last but not least, if you compare this with an, if I call it an older way of building, where you built it with point-to-point networks, and if you wanted to continue with a wavelength, you did a back-to-back connection with fiber. You had an awful amount of fiber, so the fiber management gets simplified with this as well. So to do this, it's kind of one component that makes the trick here, and that's the wavelength selective switch. So what it is effectively is a bunch of mirrors that you mirror the spectra, the wavelength spectrum that you want in the right direction. So you have a signal coming in, you split that signal up, and you mirror it back to the direction you want to use it. And if we take a more concrete example, in this case, we have 5 wavelengths coming into that, or you have a number of wavelengths coming into that wavelength selective switch, and you can then steer them out in 5 different directions. So this would be a 5-degree ROADM in this case, or 5-degree WSS. And if you look at what those looked like back in the days, it was a real mirror that you used, and you had an engine that turned that mirror to reflect the wavelengths in the direction you wanted. Then the size of the mirror was determining how much bandwidth you could actually switch each time. So then you had fixed grid ROADMs, 50 gigahertz ROADM or 100 gigahertz ROADM. Then the technology evolved. Now the most common way of doing this is with liquid crystal. So you put, a different amount of energy to the liquid crystal to turn that reflection point in the direction you want. You can do that with much smaller granularity. Typically today 6.25 gigahertz. So by combining the right amount of mirrors pointing to the direction you want, you can then get the flex grid capability. So you can turn a selectable amount of bandwidth into each different direction. So that's typically what you talk about when you want to have flex grid capability, to be able to steer a certain amount of bandwidth in the direction you want. So this is, of course, allowing you to do that. And also, in this case now, you can see that I have an uneven amount of spectrum coming in. Going out in the different 5 degrees here, I can also balance the spectrum, so it goes out in an optimized way. Because when you go through an amplifier with an unbalanced spectrum, you will actually amplify the wavelengths with an evenly unbalanced amount. So pre-balancing is a very important part of it. So this was my attempt to make this simplified. I do realize that I mentioned a bunch of abbreviations. I go into a lot of different technology tracks, but I'm going to be outside here for the rest of the event, so please feel free to come and talk to me if you have any additional questions. That was all from my side. Thank you.
Are there any questions here? No. Well, in that case, I would like to just hand you over a little token of appreciation, and thank you very much for coming and talking.
Thank you.